If body continues, sorry on the bush. If body continues in a state of rest or of uniform motion in a straight line, that is uniform velocity, unless acted upon by a resultant force. Right? This law suggests that a body which is at rest requires a resultant force for motion, and if the body is moving, a resultant force is required to increase or decrease the magnitude of the velocity. Right? All this we know already, right? Right? This here will be the basis behind circular motion. Right? So when we move on to circular motion, this is very important, right? Inertia with body is its resistance to change in motion, and therefore Newton's first law is sometimes called the law of inertia. Right? A body of large mass requires a large force to change its motion, and therefore the mass of body is the measure of its inertia. Okay, larger the object, larger the inertia. Okay, yeah, yeah. I know. Can't mess up. Well, I do my part. I want to come in. Yeah, thanks. Well, we could leave this.
Yes, online exhibit.
I know we'll keep online. Okay, let's let us play out.
Yes,
Oh, I'll give us first or second.
They're trying to get each other. Oh, that's still out.
Okay, all right, well, we'll see how it goes. We should put this up.
So we would give out.
Right. Remember the difference between mass and weight, right? Mass is the measure of inertia. Weight is the force that gravity exerts on the body, right? And you have the SI units there. Right? Remember that Newton's second law, this is the version that you have to use, right? No longer F is MA alone, right? This is the version that Ariane and I were to learn, right? Newton's second law. The rate of change of momentum of a body is directly proportional to the resultant force acting on the body and takes place in the direction of the force. All right? I have a small error there. That should be changed with time on the here, right? So force is proportional to the change in momentum of time. Right? And the set is velocity constant. We can take the velocity, right? We can take the velocity as we saw there and pull the velocity outside. If the mass constant, they can pull the mass on the outside. All right. Or if the velocity changes, then we should recognize that V minus U1t is acceleration. So you will see that F is proportional to ME, right? That's the version of we would have learned in Form 5, right? Right. Know that K is constant, but we need to remember how do you get rid of that K there? How do you get rid of that K? By giving it definition, right? If you look at the definition, right? 1 Newton is the force which produces a mass of, which produces an acceleration of 1 meter per second when a mass of 1 kilogram is acted upon, right? So if you plug in F is 1, M is 1, A is 1, you'll get K is 1. So the formula tends to F is equal to N. That's okay? Right? We'll come back to the momentum thing that's now. Right? Yeah, F equal to MA, resultant force and acceleration always in the same direction. So for example, if an object moving this way and the resultant force acting in the same direction, it means that the acceleration acts in the same direction. That's okay? What about here, Jacob? Suppose you have an object moving in a circle, right? And the resultant force acting towards the center. What direction the acceleration acting in? Same direction, right? Same direction. So if the resultant force is towards the center, the acceleration is towards the center as well. Okay? And those who did this already, where is Scholar? Where is Scholar in Petal Force? Where is Scholar result done for? Ten Petal Force, right? Nice. Right, Newton's third law, right? We know it from this small diagram here. If we have two objects in contact with each other, here's A and here's B. When object A exerts a force on object P, object B exerts an equal and opposite force on object A. So basically, F of A is equal to F of B, and they take place in opposite directions. Okay, that's Newton's third law. Right, the forces are equal in magnitude and opposite in direction, and they act on different projects, right? The satellite in orbit is an example. If you have the Earth and you have a satellite here, the satellite is able to maintain its orbit because there's a force of attraction between the Earth and the satellite, and there's an equal and opposite force between the satellite and the Earth. Okay, those forces equal and opposite, and they're able to maintain the circular path area. Okay. Right, we have that rocket, right? Linear momentum now. So this will carry us directly into linear momentum. We know that linear momentum is the product of mass and velocity. Okay, so P is equal to M by V. We know the SI unit, kgms minus 1. Anybody can help me? Where does that come from? How is that an SI unit for momentum? Well, that's close. Right. And remember, and also remember that force is what? Force is change in momentum and time. So it means that momentum is force by time. Right? So that's Newton's second. That's okay? For those who did it already, what is called that? Change in momentum is called what? Force. I think never would. I impulse. Right? Change in momentum, we're gonna look at that just now. But change in momentum is called impulse. Okay? Right. Here's what we're gonna have to do now. We have to prove this. We have to prove the principle of conservation of linear momentum. All right? And we're gonna do it together. Okay? So let's consider a few things, right? I'll do some code and we'll go through it, right? You have to be able to prove this formula, right? But here's what they looked at, right? They consider an object of mass A, an object A of mass M, an initial velocity U, that should be a U1, right? Colliding with an object P of mass M2, an initial velocity U2. The objects collide for a short time, and after collision, A and B move off with velocities V1 and V2. All right, so we have two objects colliding, right? M1 and M2, right? They collide. One has velocity U1 and one probably going this way, U2. Right? They contact with each other for a short space of time, and after collision, they move off like this, right? M1, M2, one is V1 and one is V2. Right? So we are going to attempt to see if we could take that info and come up with this principle out that we all know. What's the principle that we all know again? What's the principle that we all know? Faith? What's the principle that we all know? Before collision equals to the total momentum. Right, tomorrow what's that? Right, yes, yeah. Get right, F of A is equal to F of minus. And draw the diagram. Draw it small, I don't want to give you all that. Right. Okay, just see if we can draw a diagram and start writing. And we can do that together. Sorry? M1, M2 and the collide. Right, so once you write that, just write this first formula here. Write the formula that I gave you there. Your student came from F is equal to what? Change in momentum on time. Right, so they give you the change in momentum of M1 and the change in momentum of M2. Right, we are going to do that proof now, right? I'm going to import and we're going to finish that up. Our objective is to prove the principle of moments. Momentum, sorry. Momentum. Huh? Are we? Actually, let's put all in the same diagram, right? Let's put U1 here, let's put U2 here. And then when they collide, let's put V1 here, V2 here. All right, so let's see if we can do this together, right? Right, let's start here, Dario. So Dario, here's the problem. That's true because you want to feed them on what we talking about. All right, feed them away, so it's just not paying attention. I'll put a second time tomorrow, yeah, sure. I'll listen to you. Sure. Ready? So what is here? Ready? So here's what we need, right? We need the force applied on A. What do we know F is again? We know F is equal to change in momentum on time. Okay? So what is here? What is the, let's call this A and this B, right? What's the force exerted on A? The force exerted on A is the mass of A by the what? By the change in momentum, right? So the final is V1 and the initial is U1 all over T. That's okay? For object P, the mass is M2 and the change in momentum is B2 minus U2 all over T. Right? But remember, these are equal and opposite forces. So I'll put in a minus sign here. Right? What do we know, Jacob, when they collide? What do we know about the times? When two objects collide, the time in contact is what? Same, more than, less than, should be equal, right? So technically we can cancel this off. Right? So we'll end up with M1 V1 minus M1 U1. Applying the minus signs here. Minus and minus are plus. Right? When we reach F8, how are we going to try to find a way to show the conservation of momentum? How are we doing that? What we going to do now? Remember you told me a little while ago that conservation of momentum is total momentum before is equal to total momentum after. So what do I do here? To give us some ideas. What we could do? Fun. What we could do? Make everything equal. No. Remember, we're trying to show total momentum before these objects collide equal to the total momentum after, right? We do have that here. That's not this, but there's something that we can do real simple that would allow us to come up with that relationship. Put the U on one side and put the V on the next side. Yeah. So let's bring the, I was switching them around after, right? This is M1 V1. I'm bringing the V on this side. M2 V2. Carrying the U1 on that side. M1 U1 and I have the M2 U2. I just want to switch them around, right? I don't want to mix it up with the signs. M1U1 plus M2U2 this is the total momentum before initial end equal to M1V1 plus M2V2. So this here is the total momentum before collision, and this is the total momentum after. That's okay. So what does this say? This says that when two bodies collide, momentum is conserved. Okay, so we can definitely say that momentum is conserved. Yeah. All right, and you have to be able to show this, right? Copy it down. And let's talk about two types of collision. Right, the good form. The Google form is only for those who are not on the element, right? Ready? Yeah, it.
Right.
Two different ways. Yeah, you come to that now, right? So the next thing we're looking at is something called types of collisions. All right. So there are two main types of collisions. I'm gonna take a look at that now. Hold on. What you will notice though is make a little note that in every collision, momentum conserved. All right. Let's make a little note of that, right? In every collision, momentum conserved. So we gotta take a look, of course, we know the definition, right? The principle of conservation of linear momentum states that if no external forces act in a system, then the total linear momentum, right? In any given direction remains the same. Right? Types of collision, two main types, right? Inelastic and elastic. Right? Inelastic collisions are those in which kinetic energy is not conserved, right? Of course, the writing will note down that's right, inelastic, kinetic energy not conserved. Right? Because you have it notes, right? The kinetic energy is usually converted to heat or sound. All right. A completely inelastic is one in which they stick together after impact. You remember that? Like such as after collision, we had calculations where both objects move up together. Remember that? This is image. All right. So a completely inelastic collision is where all the energy is lost and they stick up together. Okay? Well, not all, most of the energy is lost. I don't know who is what that. I don't know. Now I'm taking it today. Right. Right. Elastic now. Elastic conditions are those in which kinetic energy is conserved. For example, gas molecules make elastic collision with each other. Right? If you have something perfectly elastic, then we'll be able to say that momentum conserved and kinetic conserved, right? All right. So if you remember that, right? Elastic, kinetic energy conserved, inelastic, kinetic not conserved. What is conserved in both of them?
Energy.
Momentum, right? Momentum is conserved in all right. Before we do anything in impulse, we have a small question to do, right?
Energy.
All right. I'll leave it out part one, right? But it says to see the law of conservation momentum, right? We're going to zoom into the rest. Part one is just KD law. Right? Part one is just KD law, ignore that, right? We are just trying to work out part two. You ever see that? I did the best I can do there, right? I'm trying to do that question, please. Please, Dario, please. Hey, hurry up now. This. You know, you just working it out, go right on, just use the values, right? Alright, so they gave you two masses, M1 and M2. Right, two objects, M1 and M2, so slowly, just check and see if any WhatsApp group now, please. Make sure see it properly. Right, two objects of mass M1 and M2 respectively, okay, nice. Right, just send me email now, I think I missed the. I think I missed this message. Two objects of mass M1 and M2 respectively, traveling in opposite directions collide. The respective velocities of the objects before collisions are given, right? U1 and U2. Assuming that the law of momentum applies. No, on WhatsApp. On WhatsApp, right? Calculate the ratio of masses M1 to M2. So you have to go back, use the principle of momentum, and see if you can make M1 and M2 the subject of the formula. Monkeys, yeah, sure. Very good. Here. Already marked M1. So with M1 by U1 plus M2 by U2 is equal to M1 by V1 plus, right? Right, all we need to do is to find M1 over M2, right? They want a ratio, right? So plug it in, let's see what you get. What I get you? Any answer? Wait, it done? What you get? Oh, not clear, taking a long, taking a long. Right, and then you have a next part underneath, right?
I can't even. I get. What did you have on M1? I have on
M1 and M2. Yeah, I think yeah, those closer.
I get them to us.
Yeah, yeah.
No, I remember that we show M1 on M2.
I get.
So M1 shouldn't go anywhere. But I think it was something close with that part. But let's see what you all get.
I get fed better.
Get 5-1.
You get fed.
Oh, right, only remember you, I would only have value for M1 here. You want to have ratio, so you gotta find a way to pull out M1 and M2, right? So you're going to get M1 multiplied by 4
Plus.
minus 3M2, correct? So we're getting sign, minus 1.5 M1, plus 5.5 M2, right? All we can really do right now, bring all the M1s together. Bring the M1 here, bring the M2 here,
Oh, I get it.
right? I have 5.5 M1 is equal to 8.5 M2.
So I do.
Huh?
I do. I use M1 from back 50. Make life easy.
So I go where M1 way.
No, it's still because I can't go with it.
Okay. Right? And then when they reach there, they want the ratio of M1 and M2. Right? So I'm moving the M2 across and I'm moving the value across. So I'm moving the M2 here and I'm moving the 5.5 on that side. So I'm kind of squeezing in the answer here. M1 on M2 is equal to 8.5 over 5.5. All? 1 and 2? Yeah. You have one outside. A short version here. Now it's long, another short one. You make it already. We are looking right here. But it's cash course all over. Right? So I got M1 and M2 as 8.5 over 5.5.
So it's
You can leave it like that. Right? You can leave it like that if you want. What's the conversion? 17 over 11. You okay with that? Okay. Online, are you okay with that? Garage, Sanya, are you okay with that? Right, we move on to the last two parts now. Oh yeah. Who got that pass with me? Oh yeah, please. Pass. M1 is 8.5, so do other math quick in your head. M2 is how much? 5.5, right? Right. Use olive powers now, and shadow. Right, so M1, 8.5, if you plug it in, you'll easily find M2, 5.5. Okay? Well, that's my dear father, I'll explain it later why it is.
You got it.
Yes, all right, this is our magic, you know.
yeah.
Right, M1. M1 is the 8.5, and M2 is what again, Sylvester? 5.5. They wanted to find the total kinetic energy before. So find the total kinetic energy before. Right? Why you find kinetic again? Right, book it out some more again before. How much you got? Oh yeah, book it out fast. Online you can message the answer, please. Katrina, some more again. Right, yeah. How much you got?
Again, they say, I could get you.
How much you got? Okay. Kinetic energy before. What? You got it? 7.5.
Make sure you can.
I just work out the kinetic energy then.
Yes.
So the board,
Yes.
alright. Other than body up there, right? Why I use, because remember, we just worked out that M1 on M2 is 8.5 on 5.5. And the question said M1 is 5.5. So if I use M1 as 5, when I work out for M2, you get 5. Why I use as B? No, that's what I do. So kinetic energy before, right? Right, that'll be a half by M1 by 4 squared plus a half by 5.5 by minus 2 squared. Remember they gave you these speeds earlier, Darian? In the seventh question, they gave you those values. So how much is this? Huh? Right, this is U. That's the speed before collision. of M1, and that's the speed before collision, right? Because they asked us to work on the kinetic energy before. How much is this here? How much you all got here? Huh? 92.75 joules, right? Yeah? Anybody else get up online? Let's see anybody get out online. 92.8, okay, that could work. Right. What they ask for after is the collision elastic? Is it elastic? Do we have enough things to determine that?
Yes.
We only have collision, energy before. Right? So we have to work out kinetic energy after. Right? We have to work out the kinetic energy after. Right? Work it out after, tell me what you all think. So quick, let me see what you got. M Ramu. Sentence. Unit 2 ahead on, unit 2 has starting. Number start later, start like and the first one. So I try to finish up module 1 and most of module 3 by the end of this term. The next term, module 3 and module 2. Right, we'll get out fast. How much you all got?
Same thing.
Same thing?
Same thing.
Are you sure? Same thing?
Yeah.
Thank you. What? Yeah, same thing. Just put nickel in that. So, Darian, look how work it out here for you. What you would say? Elastic or not? How you would say that? Because it's the same, right?
Yes.
So kinetic energy conserved, therefore elastic. So you get 17 or something. Okay, so that's the way you handle something like that.
What do you call it here? It's on side. Make it negative now, so you have to mind.
Oh, okay. And be careful. Well, that's some question that I plug in the value. But okay online there? Right, are you okay?
So I'm not concerned. Like what? What you? I want to be on
What? I didn't want that 3 down.
So you know the song was He married to secretary, so he also did the job.
He didn't really want to. He leave like 2 years. Yeah.
Like official vacation.
Vacation, yeah.
And we can also it's extra money like stuff right. This was and got the goal is every class I listen to the class week. I see every single class. I just pick on the ups now. This is here.
Alright, let go back now.
Yeah, I think.
Mr. Abdul.
Yeah.
Abdulman?
Yeah.
And what is it?
You got it.
Why the trap? When else? No, I don't think I didn't want to. Right, let's continue. Let us look back again, make it through. But when I demo transfer. And we want to know. Alright, let's continue. Let's take a look at this new term called impulse, right? What is called impulse again, Daria?
You change the momentum.
Something at the end, right? Alright, so let's move on to this last new quantity called impulse, right? Yeah, Marquis, yeah, the impulse, so look at this now. Alright, impulse. So the impulse of a force is the product of the force and time. Alright, so if they have to define impulse, it's simply the product of the force and time. Right, here's the next small definition. If you use Newton's second law, you'd also see that impulse is change in momentum. Alright, just make a quick little note of that. Impulse, force by time, impulse, change in momentum. Right, why is this impulse quantity so important, right? Something that we experience on an everyday basis, right? Once there's a change in momentum, you must have an impulse acting. All right, so once a force acting for a period of time, you will have a impulse. Actually, I made a say I keep worrying about it.
Like it took it so to you and the the guys. Yeah, you know, probably.
Big note.
Yeah,
big,
A big note.
Yeah.
We have to keep that one. And if I want to have it,
Yeah.
it's very enough for. All right, so the term impulse. Right, the term impulse is usually associated with a force which acts for a short time. All right, so just remember this in all our examples. Remember that impulse is equal to force by time. So normally it's associated with a force acting for a short time, or sorry, a large force acting for a short time, or the other way around. A small force acting for a long time. All right. However, it can be applied for smaller forces which act for a long time, right? So when an object undergoes a momentum change by an applied force, the applied force may be large for a short time interval and still produce the same change in momentum. All the same is this. All the same is this, right? If I have a large force acting for a short time, that will produce the same change in momentum as a small force acting for a large time. Right? These two will produce the same impulse. That's all it's saying, right? But it's more popular faith It's more popular for what? It's more popular for to have a large force acting for. Right. Think about this example here, only. Jumping with your knee bent. How does that help? Huh? How? So, alright, so it reduces the force and does what? So when you jump, right? You have a mass. When you jump, you have a mass, right? And there's definitely a change in momentum. Right? Right. So what you want is you don't want that force to be larger than your knees, right? But what happens if force larger than knees are? Monkeys? What happen? What happen? Your knees will? Right. So here's what? What we will end up with is a short force. Sorry, a small force. A small force acting for a long time. So for example, when you jump and you land on the ground with your knee bent, it will take a longer time to straighten up, right? So what will happen there is a longer time with you being in contact with the ground. No examples, right? So therefore, that's one of the reasons why you jump with your knee bent. If you try to jump with your knee straight, you're gonna have a larger force in a short time, right? And you can end up damaging your knees, right? Darian, so you alone. Explain number 2. Airbag. How does the airbag help? During a collision. What does the airbag do? No, tell me. How does the airbag help? During a collision. In terms of impulse, I'm talking about. Yeah.
No, you can't. No. When you move it, when you stop, you come to certain stuff. You body will continue. But then, when you have the opposite momentum, then you achieve the momentum. Your body
I like that. Wait, am I?
I'm kind of
Nah.
Wait, no, but so big,
Go ahead.
right? So you then you turn. That music is also so wait, because
Yeah.
Right? Remember, we want to know how.
Your body will continue. Your body will continue moving at a constant velocity.
Right, so how does the airbag help reduce?
So, living here back here, why?
Right, so in the airbag, Marquis, it's now about 2 minutes, boy.
I didn't check anything.
Alright, so here's what is happening, right? During a collision, of course, there's a change in momentum and there's a mass, right? But of course, you don't want that force to be large on you. So what the airbag does when the airbag deploys, right? Well, what the airbag does in this case here, the airbags, right? The airbag increases the time that you will be in contact during collision. Therefore, the force is deployed. But yes, technically, we consider your velocity as the goal alone, right?
Because when the airbag push on the air on the
Yeah.
as opposed to the
Right, so the airbag increases time interval for impact, therefore decreases the force, right?
That's why I say those. I say that.
Somebody did it.
Alright, so what will happen? The airbag, when the airbag deploys, what will happen is that it increases your time in contact with the collision. So the airbag will be in contact with you, right? So it increases the time that you are in collision for. So therefore, what will happen is that a small force will be acting on you during that change in momentum. But if you remember, we can't change that. There is going to be a change in momentum, right? Right? And remember, change in momentum results in a force acting over a period of time. Right? So if you can't change in momentum, what we want to do is make sure the force is small. So the force is small by keeping it on time during the impact. Alright? Hello, okay with that concept online? Katrina, Soraya, listening? Right, finish. Take a look at this, here, right? Finish. Let's say we plot this graph. Yes. Right? Let's say we plot a graph of P versus P, and it looks like this. Right? P is momentum. P is momentum, so the momentum versus time graph. Right? According to that small equation there, what does the y-axis give you? Y-axis. Look at it there. Here is the y, here is the x. Oh, so this is your C. So your right. So your y-intercept gives you the initial momentum, and what does the gradient give you? Gradient. Gradient. So the gradient is your force. What's right there? What's the gradient? Right? This is your y-axis. This is the x-axis. This is your gradient. This is your y-intercept. Right? So it's important that if you get a momentum versus time graph, you know what gradient and what the y-intercept will give you. All right? All right. Right? This came in a multiple choice. I'm sure you know. Right, and one last thing, if I give you a force versus time graph, what is the area here represent with? Yeah, Faith, what does the area on the force time graph give you? Yeah. Right here, Faith. Right? Area on the force time graph is total momentum change. Which is impulse. All right. All right. We have one little graph to draw, right? I'll give you the scenario. I want to draw this graph in a head-on collision, right? Oh, sorry. Right, here's what you're doing for me. I want you to draw the graph. For two cars that underwent a head-on collision. Right? Draw a graph representing, a graph representing two cars undergoing a head-on collision. Yes, force versus time graph. Force versus time graph for cars that underwent a head-on collision.
With doing. Oh.
Yeah. I would like a force with time graph for two cars that underwent a collision, equal mass, they underwent a head-on collision. See if we can sketch what you think the graph will look like. Force versus time, right? Then during the collision. Try that password there. Sketch a graph of force versus time. Remember, area under force time graph is what? For changing momentum, right? And the change in momentum supposed to be what?
Well.
Right? Supposed to be equal. So keep that in mind before you sketch the graph, right? Try something with a pencil. Right? Our next topic is one of the most popular and fast paced, but it's circular motion, right? So I'm going to send you a next handout with circular motion questions on hard and easy and fast papers, right? I'll send that page for next. I might send this because central going to you.
I realized from the
Try and see what your graph will look like. Please remember that the areas under the graph should be what? And it should be equal or not?
So, how big of what's something?
No, I think it's circular motion. I should look that. Alright, so I'm gonna put some more in. Yeah, but I'm not right there.
That's one thing.
Right, and I'll give you some more info. So at any instant during collision, the forces acting on the cars are equal. That makes sense? But opposite in direction, right? So this means that the graph will have the same shape and size. So whatever shape you're drawing should be the same shape for A and same shape for B, but in opposite directions. So one will be positive and one will be negative. So one will be above the graph, one will be below the graph. So you're confident? Yeah. Right. No, you only consider during the collision. Just before it's collided, it had no force on it. And then there was a force and then there was physical kind no, that's always. Yeah. And like a V shape underneath, upside down V on top. Something like that. But you gotta be a little precise with something.
I got. Is this sketch? Is this sketch?
Right. What about the area under the graph? What about the area under the graph? Would it be the same?
Yes.
Yes. So the area of A and B are equal in magnitude but opposite in sign, which means that the impulse of both cars are equal. That makes sense? The impulse equal, right? The momentum change for each car is equal in magnitude of that. All right. So your graph technically, I'll try and get them. Might look something like that. Right? Because if you remember, at some point it has no force, then there'll be a max and then it will go back to 0. Right? So the area here and the area here should be exactly the same. So your graph will look something like that. Even if you had just somebody to take it, huh? Here's the and here's. If you had that, right, but there's a point when enough you have no force to that. Okay, so that is your that's what the graph will look like. Right? Remember the areas underneath have to be identical, right? What's your name? Solid? You okay with that?
So you know when you pull a salad, you can hear you, right? Is that boy?
Ah, one boy from France, one boy.
Really?
Alright, so what we do next week Friday, not class.
No class.
So,
Yeah, so Saturday.
On what? Americans? Wait, you sometimes see it? Subject.
Now I know. If I didn't know, if I didn't know, you anywhere.
Well, I'm supposed to say I should fit. Just because I take longer, so then I should fit.
Alright. Right, I know we don't have much time to do the whole thing, but let's see if we can do part 1 and 2 now. But you see anything? Let's try, we can talk it out a little bit, right? We'll start with Darian, since I can talk so much. Right, in a crash test, a car mass 1200 kilograms hits the wall and recoils. The initial velocity is 20, it bounces back at 1.5. The contact with the wall lasts 0.18, right? What's the change in momentum of the car area? What is sign change in momentum? You can also find change in momentum. But and we have the mass. And we have the initial velocity. And we have the final velocity. So we can find the change. Yeah. Right. Fires get impulse. Please remember I have a sign change, right? Fires find impulse again, please. FT, but we don't have F again.
MV minus M.
Right. So part 1 is here. Now we realize that?
Yeah.
Get your name. Shazana. Shazana. Fires find impulse. Well, just like that, right? MP minus M. That's okay. Sketch the graph to show the typical variation of force with time during the collision and state what the area is. What do you think the graph will look like?
So,
State the media slope, right?
Yeah.
The graph will look like that. And what does the area represent? Impulse, right? Area is impulse. All right.
so if I did area action.
Well, you want in a question, you want to count the blocks. Right, just do my favor, screenshot and send in the group and finish it over.
So you screenshot this up. If I screenshot this up.
So stop somebody on. Katrina, get it as screenshot and send it to you.
So I was definitely do this for you. Yeah, I swear it's not that
No, it's good, good.